Okay, welcome back once again. Now we're going to continue with the stability properties of linear systems. For this, let me open a new page and let's do stuff. So for stability discussion, I'm directly focusing on 2x2 systems. All right, so our system is something like that. We have x dot t, a11 xt, a12 yt, plus b. But let's suppose we look at the normalized system because there's no difference. And y dot t equals a21 xt plus a22 yt. Again, this material is directly from Takayama, I believe it is chapter 7. Okay. Now, in shorthand, of course, you have here the matrix A11, A12, A21, A22. Okay. Now, what do you know about linear systems is something like that. So if I'm just looking at one variable, okay, and if it is, let's say, phi times xt, I know that there's exponential growth here, right? So the solution is something like this. So I assume that there's a solution, let's say C1, C2t, right? Then I realize x dot t is equal to C2, C1, e to the C2t, right? So if you equate this with phi xt, you realize that phi is, so C2 is just equal to phi, right? Now we're gonna start with something like this, but now we have two variables, right? But still the system is linear. So as a heuristic, we start with something like that. So suppose that xt is equal to cx e to the lambda t and yt is equal to cy e to the lambda t. Now, obviously, I don't know what lambda is, right? And I don't know what cx and cy is. In general, cx and cy, these are any real numbers, by the way. These are some real numbers, and lambda is also unknown. All right? So now if these are true, then what do I have? I have x dot equals lambda cx e to the lambda t, and y dot equals lambda cy e to the lambda t. In other words, if you look at it carefully, I have this and I have that. If these are really solutions, okay, if these are really the solutions, then I have something like that, all right? So if I take these as being true, I have something like that. Lambda xt equals a11 xt, a12 yt, and lambda yt equals a21 xt, a22 yt, right? Because these are, so this is x dot t, this is y dot t. Now this, if you look at it carefully, is also a linear dynamical system, which is homogeneous, right? So I can write this as this one. A11 minus lambda, A12, A21, A22 minus lambda, right? Times xt yt equals 0. Now, if the solution is exponential, so that my differential equations are linear, then for some lambda, I'm going to have xt, yt as the vectors. Now, these lambdas are called eigenvalues, and these xt, yt vectors are called eigenvectors. Okay. So for this to have a non-trivial equilibrium, okay, for this system to have a non-trivial equilibrium, and by non-trivial, I mean xt different than 0, yt different than 0. This further requires cy different than 0, cx and cy different than 0. Okay? This further requires that. Now, for this to occur, I need this determinant, okay, determinant of this matrix, and this matrix, if you look at it carefully, is A lambda I, right? This determinant must be equal to 0. Okay? Why? Well, if this determinant is not equal to 0, the slopes are different, right? If slopes are different, the only solution is at 0, 0, right? If you think about linear systems, you have one equation here, all right? And if slopes are different, you have another equation here. If slopes are different, then you have only one solution, which is at 0, all right? For this reason, we want slopes to be the same. For slopes to be the same, determinant must be equal to 0. Okay? Determinant must be equal to 0. So I look at this matrix, and I want this determinant to be equal to 0. So in other words, we have this to be equal to 0. Now, this equation is called the characteristic equation. Characteristic equation of matrix A. Okay? So if you write this explicitly, you have A11, A22 minus A11 lambda minus A22 lambda plus lambda square minus A21, A12. So yeah, then you have lambda square minus A11 plus A22 lambda plus A11, A22 minus A21, A12. Okay? Now, if you look at this carefully, this is the trace of A, and this is the determinant of A, right? Now, in what follows, we're gonna call this P, and we're gonna call this Q, okay? So, the solution to your characteristic equation in a 2x2 system will give, in any n by n square matrix, will give you the eigenvalues. Now, typically, of course, since this is a polynomial equation of polynomial degree 2, you're going to have 2 eigenvalues. All right, because you have 2 variables, your system is 2x2, then your characteristic equation is quadratic, then you have 2 eigenvalues as the solution of this characteristic equation. Okay? And depending on these eigenvalues, now realize that, of course, eigenvalues could be real number, they could be complex numbers. Okay? And the complex number, if you recall, a complex number has 2 parts. One is the real part, right? A is real, and the other is imaginary part. In the imaginary part, B is real, and I is such that I squared is equal to -1, right? Complex numbers. So depending on the values of these eigenvalues, depending on the sign of them, depending on whether they're complex or real, etc., you're going to have the stability results. All right? Now, we had this example system, which we linearized. So it was 6x minus 4y minus 2x minus 4y. Okay. So x dot equals 6x minus 4y and y dot equals minus 2x minus 4y. So your characteristic equation, so your A matrix is 6 minus 4 minus 2 minus 4, right? So your characteristic equation is determinant 6 minus lambda minus 4 minus 2 minus 4 minus lambda equals 0. So you have 6 minus lambda times minus 4 minus lambda minus 2 times minus 4 equals 0. So if you solve this, you're going to find your lambda. So how do you do that? So minus 24 minus 6 lambda plus 4 lambda plus lambda squared minus 8. Okay, equals 0. So you have lambda squared minus 2 lambda minus 32. Okay, right? So you have lambda 1, lambda 2, 2 plus minus 4 minus 4 times 32 divided by 2, right? So as you realize, your roots are complex, right? Because this is negative. No, wait. This must be positive because it is 4 times A times C. Your C is positive, so you have that. And then there's a positive root there. Maybe both roots are positive, depending. Yes, both roots are positive here, right? And real. So lambda 1 is greater than 0, and lambda 1 is real. Lambda 2 is greater than 0, and lambda 2 is real, for instance, right? So you can easily solve for 2 by 2 system. The system could be 3 by 3. The same will happen, right? Your polynomial equation, your characteristic equation will be of order 3. Then you're gonna have 3 eigenvalues. Remember one thing about polynomial equations. Your roots could be equal, all right? Depending on your system, your eigenvalues could be equal to each other, all right? For instance, if this is your characteristic equation, right? How many roots do you have? You have 3 roots. And all of them are equal to 2, okay? So now I will give you the theorem. I think it is theorem theorem 7.3, okay? Theorem 7.3 for the system x dot equals ax 0, 0, is, yes, so first item is 0, 0 is asymptotically globally stable if and only if both lambda 1 and lambda 2 have negative real parts. So what does it mean? So in general, you write your lambda 1 as A1, B1I, and A2, B2I, right? So of course, if B1 is equal to 0, lambda 1 is real. If B2 is equal to 0, lambda 2 is real, right? Not complex. But here, I give you the global stability result as an if and only if statement. So it requires both lambda 1 and lambda 2 have negative real parts, right? So we require A1 is less than 0, A2 is less than 0. So your model could have real or complex eigenvalues, but global stability requires the real parts to be negative. Okay? That's the first item. Because again, if B1 is different than 0, lambda 1 is complex. If B2 is different than 0, lambda 2 is complex. But global stability result in the first item that we have here requires only the negativity of the real parts. Okay? So let me lose them. And continue with the second item. 0, 0 is, so 0, 0, so let me use the exact statement of the theorem. Spiral trajectories are obtained if and only if lambda 1 and lambda 2 are complex, but not purely imaginary. Okay? What does it mean? So here in the second item, we require B1 different than 0, B2 different than 0, but A1 and A2 also different than 0. Okay? So this means they are complex. This means they are not purely imaginary. Okay? Because if A1 is 0, A2 is equal to 0, these numbers are purely imaginary, pure imaginary. Okay, we don't want that. We want both the real parts and the complex parts. Okay, and the imaginary parts. There is an addendum here. If they are purely imaginary, then the equilibrium is centered. Okay? So remember, these are spirals, right? These are spirals, and this is centered. Okay? Don't forget. So 3 0 0 is a saddle point if lambda 1 and lambda 2 are real and have opposite signs. Okay, so we require if lambda I is greater than 0, lambda j should be less than 0, where both lambda I and lambda j are real. Okay? In that case, it's a saddle point. Then we have 0.4, 0, 0 is a node. So this is also if and only if. If and only if lambda 1 and lambda 2 are real and have the same sign. Okay? So if both are positive, it is called a node. If both are negative, it is called a node. And obviously, if you look at item 1, you can see that if they are both negative, it is a stable node. If they are both positive, it is an unstable node, right? Because it tells me just that. And if you compare, if you combine item 2 with item 1, you can also see that for stable spirals, you have negative real parts. For unstable spirals, you have positive real parts. Okay? So in general, we require real parts to have negative signs for stability. Okay? And then there are different types of the system. So it is, I don't want you to memorize all these things, but once you keep on working, then you learn. You learn and you remember why it is saddle, why it is spiral, why it is a center, etc. Okay? Now there's another theorem. This theorem is theorem 7.4. So it says this: for x dot t equals axt, 0, 0 is asymptotically globally stable if and only if trace is less than 0 and determinant is positive. Okay. Additionally, zero, 0 is a saddle point if determinant is less than 0. Okay. Now, finally, remember that trace is P and determinant is Q. Now, we also have this for the 2x2 systems. Trace is going to be the summation of the eigenvalues. Determinant is going to be the product of eigenvalues. Okay? So this is a highly important shortcut Why? Because you can now easily write the characteristic equation. You don't have to do A11 minus lambda, A12, A21, A22 minus lambda equals 0. Instead of this, you're just gonna write lambda 1 plus lambda 2 equals P, lambda 1, lambda 2 equals Q, and then you have two equations and two unknowns. Okay? So at the end point, of course, you're gonna find the same eigenvalues, whichever method you are using. All right? So let me tell you one further thing. There's a very nice figure in your textbook that summarizes many stuff that you see. So let me just find it first. Okay. Let me just find that figure. Somewhere in chapter 7. I know that. I'm going to tell you the page number. Oops. Okay. All right. So I have to go by hand. Where are you? Yeah. So it is on page 408. Okay. Let me show you this very quickly. So I can actually draw it. So in that figure, this is Q, and this is P. So Q, remember, is equal to the determinant, okay? And P is equal to the trace. Now we have something like this, right? What is that? This is P squared minus 4Q. This is inside the solution, right? Because if we are on this side, if P squared is greater than 4 times Q, then the roots are real. Then if it is less than that, the roots are complex, okay? Now, what do we have? Here we have centers. Okay? We have centers here. Basically, P is 0 and Q is positive. Here we have spirals. Let me just double check. Yes. P squared minus 4Q. So okay, here we have stable spirals. Here we have unstable spirals. Okay. On this, so if determinant is less than 0, where are my nodes? I'm looking at my nodes. Okay, so nodes are here. and these are unstable nodes, and these are stable nodes. Okay, saddle path is somewhere here. Okay, so this part is asymptotically stable. Why? Because trace is negative. When trace is negative, since it is the summation of eigenvalues, right? If it is negative, this is stable, and this part is asymptotically unstable. This is also unstable, exactly this point where Q is negative and P is 0, right? And here we have saddle points because one is positive, one is negative. Okay, so we don't really know, right? If trace is if trace is 0, then we look at the determinant, because determinant being negative tell me it's a saddle point. Okay, so this is at page 408, Takayama. I mean, this is just basically theorems 7.3 and 7.4 combined. Okay. Now, we have about 4.5 minutes for discussion. So once again, let me summarize this to you. So if you have the nonlinear system, one thing you can do is to linearize it, right? After linearizing it, then you can find a normalized version of it. So you basically move the steady state to 0, 0. Then you find the eigenvalues of the characteristic equation, or you can write the characteristic equation of the matrix A and find the eigenvalues. Then after finding the eigenvalues, you can tell me specifically, using theorems 7.3 and 7.4, you can tell me exactly what type of equilibrium is that and whether it is stable or not. Okay, that's the entire idea. Remember, if you do not linearize the model, you can still find the phase diagram. And in the phase diagram, you can still tell me in each region how the system behaves. But we cannot sometimes be sure about the type of equilibrium. For instance, if we have spirals, we cannot tell whether it is a center, whether it is a stable, unstable spiral, or whether it is an unstable spiral. Sometimes we cannot find that. All right. So there is a trade-off. If you linearize the model, you tell me something very accurate, but only true around the steady state. If you do not linearize the model, you can tell me something a little bit vague, but it is true for everywhere. Okay. So that's the entire analysis of continuous time dynamical system. So beyond that, starting next week, we're going to look at dynamic optimization. So we want to understand now for these models, for these x dot equals ax plus b models, there is no economic decision yet, right? Now we want to create economic problems where agents face dynamic trade-offs. Okay, not just static trade-offs, but dynamic trade-offs. So under dynamic trade-offs, they're going to take their decisions so that at the end, their decision is going to be reflected by a dynamical system. Okay? If there's a consumption decision and saving decision, then I'm going to find a two-variable system of consumption and wealth, for instance. Okay? Starting next week, we're going to see these things. Now, we can meet again today for your questions and comments if you have any, because we have about 1.5 minutes. I have time. That's not a worry. Speak up, people. Speak up. Do you want to meet after?
Question.
Do you want to meet after this session ends? Or it is all okay? Again, I have time. I can answer your questions. I can hear your comments.
It's all okay for me.
All right, since nobody is speaking up, I assume that everybody is happy with the material. Everything is clear. Everybody understood what I discussed. Again, this is very familiar, very simple thing, but you have to make peace with the notation. You have to sit down. You have to write down. You have to solve the problems in the textbook. You have to solve the problems in my website. All right?
Okay.
All right, so then,
okay, thank you.
Then I'm gonna see you next week, and we're gonna look at optimal control theory. It's a better thing for you to, I mean, it is advisable if you check the textbook to gain some familiarity before the class, okay?
Okay.
All right, bye-bye then.
Okay.
Thank you.
See you.
Bye-bye.
Thank you.